Good morning, everyone. I want to welcome you to the National Advisory Environmental Health Sciences Council meeting here on September 11th, 2024. So calling to order, and I just wanted to remind everyone, pursuant to the Government in the Sunshine Act, all aspects of this meeting are open to the public except the review, discussion, and evaluation of grant applications and related information. So I want to welcome all members of our council, welcome all of you to this council meeting. We've got a packed agenda. We're going to be talking about some very exciting science, and then David and I will talk about the strategic plans from the past as well as the strategies for the future. So David, let me turn it over to you.
Thanks, Rick. So we'll get started today with introducing our council members. So I will just go through an alphabetical order and let everyone come on camera and introduce themselves to everyone. So first up is Stefania Cormier.
Sorry, I was already on. Hit the button. Good morning, everyone. Stefania Cormier. I'm at Louisiana State University. I am the Associate Vice President for Research with specific focus on human health and data safety. And I study respiratory exposures, including pollution from Superfund hazardous waste sites and from respiratory tract viral infections, and how the intersection of those two lead to long-term airways disease. And I'm director of the Louisiana State University Superfund Research Program. Thank you.
Thank you, Steph. Tim?
I'm Tim Greenemeyer at the University of Pittsburgh. I'm a neurologist and neuroscientist interested in gene-environment interactions in the causation of neurodegenerative diseases.
Thank you, Tim. Andre?
Can you hear me?
Yes, we can.
Andre Holian, University of Montana, Director of Center for Environmental Health Sciences. I'm primarily interested in respiratory toxicology to understand the mechanisms of development of chronic inflammation.
Thanks, Andre. Daryl?
Good morning, everyone. Daryl Hood, The Ohio State University, of course. I am a professor, Dean's Fellow, and principal investigator. I'm the co-architect of the Public Health Exposome framework and analytics, and so, which is fastly gaining traction. Good to see everyone. Thank you.
Thank you, Daryl. Is Carrie on? I didn't see Carrie. So I think Carrie Hornbuckle from University of Iowa will be joining us later in the day. Catherine Hoya? I saw you on. Yeah.
Yes. Hi, I'm Catherine Hoya. I am an epidemiologist. I'm at North Carolina State University. I study environmental contaminants and the response by the epigenome and diseases throughout the life course. Right now, the main outcome we are looking at are liver diseases.
Thank you, Catherine. Jenny?
Yate Abene, good morning. Jenny Ingram from Northern Arizona University. I'm an analytical chemist by training, but do environmental health studies out on tribal lands, which I happen to be on Hopi right now in Tuba City, Arizona. And I will be dropping off this afternoon because I have some meetings with some community members out on Navajo. So it's great to be here.
Great. Thanks, Jenny. Is Tom Leveist on? So I think Tom will also be joining us later in the day. Gary?
Gary Miller from Columbia University. I'm Vice Dean of Research and Professor of Environmental Health Sciences, and I work on exposomics, neurodegeneration, and many other diseases.
Thanks, Gary. Gökhan?
Hi, I'm Gökhan Mutlu from University of Chicago. I'm the Chief of Pulmonary and Critical Care and the Director of the Respiratory Biology Training Program, which is funded by NHLBI. My lab studies the mechanisms by which particulate matter air pollution causes cardiopulmonary disease.
Thanks, Gökhan. Maria. I don't see Maria on the Zoom either. So Maria Savasta Kennedy from UNC is also going to be joining us later. Yulia, our ex officio members. So Yulia Carroll.
Yes. Hi, everyone. This is Yulia Carroll. I'm the Associate Director for Science at the CDC's, the Centers for Disease Control and Prevention Division for Environmental Health Science and Practice. And the CDC division where I work prevents exposures to environmental health hazards, and we achieve this by surveillance, epidemiology, technical assistance, training, and preparedness activities. Thank you for being here.
Thank you, Yulia. Susie?
Susie Fitzpatrick from FDA, and I work really closely with NIH on contaminants of emerging control as the co-chair at ICFAM and a lot of other research projects. And I'm really happy and honored to be here as part of this meeting and look forward to a really, really good meeting.
Thanks, Susie. And Annette?
Yes, good morning, everyone. Annette Giuseppe Eli. I'm with the Office of Research and Development with the U.S. Environmental Protection Agency. I'm our National Program Director for Chemical Safety for Sustainability. I'm subbing here for Andrew Geller, also with ORD, and pleasure to be here. Looking forward to the duties. Thanks.
Thank you, Annette. We also have 3 ad hoc members of council that will be joining us, hopefully permanently on council in our February meeting. So they are able to join us for the discussion today and tomorrow, includes in closed session, but they will not be voting members of council. So the first of those is Dr. Bevan Engelward from MIT. She will not be joining us. Oh, I see Maria is on. Maria, would you like to introduce yourself? You're muted. Closed session, but they will not be voting members.
Sorry, are you all able to hear me?
Yes, we are.
Okay, sorry about that. I've got some repeats going on in the background. Maria Savasta Kennedy here from UNC School of Law, where I'm a clinical professor. I run our internship program and I teach students environmental justice. Are you all able to hear me?
Yes, we are.
Okay, sorry about that. I've got some repeats.
Yeah, you may be on the webcast as well, Maria, so you may want to turn that off and just be on the Zoom.
Anyway, good to see all of you. I run our internship program and I teach students environmental justice.
Okay, so the second is Patricia Nez Henderson, who I also think is not on with us. Patricia, are you here? And then the third is Cheryl Walker from Baylor College of Medicine. Cheryl. So they may not be on just yet. And then we have 2 members of council who are not able to join us for this week's meeting, for the September meeting. That's Phil Bourne from University of Virginia and Olivier Deschênes from UC Santa Barbara will not be able to join us for this meeting. Then I would like to start introducing our members of the NAEHS Senior Leadership Committee. You've already met Rick and myself. So Trevor, would you like to introduce yourself?
Happy to do so. Good morning, everyone. I'm Trevor Archer. I'm the Deputy Director at NIEHS and an NIH Distinguished Investigator. I'm a biochemist by training with interest in epigenetics and stem cell biology.
Thanks, Trevor. Gwen?
Good morning, everyone. Gwen Coleman. I'm the Director of the Office of Scientific Coordination, Planning, and Evaluation, and I'm the Strategic Lead for Coordination for the NIH Climate and Change and Health Program.
Thanks, Gwen. Mike?
Good morning, Mike Fessler. I'm Acting Clinical Director since July 1st, physician scientist with a pulmonary critical care background by training and training in immunology. And I look forward to the proceedings today. Thank you.
And J. Ingrid Mathis, our Executive Officer, I don't believe is with us today. I think she's tied up in other meetings. Is Robbie on, her deputy? I don't think so. Heather is next.
Morning, everyone. I'm Heather Pattisall. I'm the Scientific Director of the Division of Translational Toxicology. I'm a developmental neuroscientist by training and do a lot of work on endocrine disrupting chemicals. Nice to see everyone.
Thanks, Heather. And last but certainly not least, Daryl.
Good morning. I'm Daryl Zeldin. I'm the scientific director, and I ran the Division of Intramural Research. I'm a pulmonary critical care physician scientist. Nice to see everybody.
Thank you, Daryl. So now turning to more administrative aspects of the meeting, just a reminder that this meeting is being conducted in Zoom, and so we want to follow our standard Zoom etiquette. So the meeting is being webcast, and it is important that all of us on the Zoom keep our microphones muted whenever we are not speaking to avoid any background noise or accidental broadcasting of conversations that should not be broadcast. You can use the raise hand function in the Zoom meeting, and I will be moderating most of the discussion through the day. Just to preserve bandwidth, we encourage you to turn your video off while you're not speaking. And when we have council discussions, we will encourage all the council members to turn their cameras on so we can be a little bit more interactive in those. Make sure that you keep your VPN turned off unless you need to have it to access systems. At times when council members need to be absent from the discussions, as for instance, for a conflict of interest reason, they will be electronically put into a Zoom waiting room. So Nathan and the AV folks will manage taking you out of the conversation, putting you into a waiting room. You do not need to leave the Zoom session itself. We'll bring you back into the conversation when we've are done with that particular item. Any members of the public who wish to express any views regarding any of the items being discussed during the open session may do so by sending an email to the council using the address listed on the council webpage. And I think Nathan will periodically raise that during the webcast. That is national.advisory.council@niehs.nih.gov. And Ashley, Valerie, and I will be monitoring that email during the council session. A reminder for council members that we will be voting at various times throughout the meeting, and those votes are conducted electronically using the electronic council book, which all of you have access to on the tab that is called Agenda for Use During the Meeting. That will have hot links to all of the items that we are voting on, both in open and in closed session. With that, I will turn over to the review of confidentiality and conflict of interest statement. So this is a reminder that policies and procedures for preventing conflict of interest and confidentiality of grant materials are contained in the conflict of interest forms that have been emailed to you by Ms. Valerie Bartlett. In that document states that this certifies that in the review of applications or projects conducted by the National Advisory Environmental Health Sciences Council on September 11th and 12th, 2024, I exempted myself and I did not participate in the discussion of nor vote on any applications or projects in which I, or to my knowledge, my spouse, minor child, or close professional associates have a financial interest, nor on any applications or projects from an organization or institution where I am an employee, consultant, officer, director, or trustee, am negotiating for employment, or otherwise have a financial interest. In council actions in which we voted on a block of applications or projects without discussing any individual one, the en bloc actions, my vote did not apply to any applications from any institution fulfilling the criteria in the preceding paragraph. Members should sign the certification and email them back to Valerie at the end of the session. And with that, we'll change to our first voting action of the day, which is the consideration of the minutes for our June 2024 Advisory Council meeting. So these minutes are available on the NAEHS webpage, and council members were asked to review them before this meeting. They are also included in the electronic council book for councils to review. So I would like to ask for a motion to consider or to approve the minutes from a council member.
I so move.
Thank you, Steph. And may I have a second of that motion?
I second.
Thank you, Maria. And if council members could please log into the ECB and vote to approve the minutes. And actually, if you could let me know when we have quorum.
So just a reminder, you all want to be on the For Use in Meeting tab, and hopefully you can scroll down to the bottom where there is a link directly to the meeting minutes. You click on that and you should be able to vote yes, no, or abstain.
Ashley, Valerie, how are we doing?
I am honestly unable to see who's voting. I keep getting the wheel, so that's not good on my end. Valerie, are you able to see?
Still checking.
Maybe for the interest of time, we should do an old-fashioned hand vote.
I think that
I see 6 total yeses.
Oh,
Okay.
good. Someone
I don't
can
have
see
a
them.
circle.
Good.
I can see them. I can share my screen if you want.
Thank you, Steph. No, that's completely fine. It's probably something with our NIH VPN. So I think we have.
I confirm. I see 6 voted. Yes.
Okay.
Excellent.
Super.
Thank you. And just this is more relevant in the closed session where we will be voting more often. But this is a reminder to council members that the ECB will time out after 15 minutes of inactivity. So you should keep your login information close by to facilitate the voting in the ECB. And then a final reminder is to note the following future meeting dates for the Advisory Council. The dates are listed on the ECB on the Council Information tab. They're also listed on the NAEHS website. Our next meeting will be a virtual meeting on February 18th, 19th of 2025. And then the meeting following that will be an in-person meeting, June 4th and 5th of 2025. So that'll be back in the Rob Bell Auditorium in North Carolina. And then the future dates for September 25th, February 2026, those meetings have also been scheduled, should be on your calendars, and we'll provide more information as we get closer to those dates. With that, I'll turn it back over to Rick to introduce Dr. Bertinelli.
I think we have Patricia's hand up before we move.
Yes, so thanks, Ashley. Patricia.
No, I was just trying to figure out how to vote. Sorry about that, everyone.
No problem. Thanks, Patricia.
Okay, well, let's keep things moving along. So it is with great pleasure, and it's a real honor for me to introduce our first speaker today. Is Dr. Monica Bertinelli, who is the NIH director. So Dr. Bertinelli is the 17th director of the NIH, and she began her tenure last November 2023. So she previously served as the 16th director of the NCI, the Richard E. Wilson Professor of Surgery and Surgical Oncology at Harvard Medical School, a surgeon at Brigham and Women's Hospital, and a member of the Gastrointestinal Cancer Treatment and Sarcoma Centers at the Dana-Farber Cancer Institute. So the week after she started her tenure as NIH director, I had the opportunity, the honor to meet with her in person on the NIH campus. And I'll never forget that event. When I walked into her office, she stood up, she greeted me with a handshake and a big smile, and asked me to tell her more about the work that we do at NIEHS and how we study the environment. So most of all, she shared her vision with me at that meeting, which most notably involves and you're going to hear more about this, it involves better integrating the work across the 27 institutes and centers and the various offices within the Office of the Director. And you will hear that this is very much in alignment with my vision for NIEHS. You'll hear that when I talk about our strategic plan tomorrow. So I've thoroughly enjoyed working with Dr. Bertinelli. I know she is bringing strong leadership that we all need at the NIH. Now, she was hoping to be here with us in person, not in person, but virtually with us. But she's actually out doing her job representing the NIH in meetings with senior officials in the US government. So it's good that she's doing what she's doing. That benefits us all. So she has promised to visit us in person at some point in the near future. But for today, she has sent a video. And so without further ado, I'm going to turn it over to our colleagues in the IT booth to play the video from Dr. Bertinelli.
Hello, everyone. I'm Monica Bertinelli, and I am honored to be speaking to you today as the 17th Director of the National Institutes of Health. When I got the call asking me to come work at NIH, I did not hesitate to say yes. As a researcher and a clinician, I've always admired NIH, and I'm thrilled to be in a place where everything we do revolves around a single goal: improving the health of all people. Our job at NIH is clear, even if it's not straightforward. We are here to seek fundamental knowledge about living systems and to apply that knowledge to enhance health for everyone. As NIH director, I'm concerned about disturbing trends in the overall health of the American people. Life expectancy in the US is low compared with our peer nations, even though we spend much more than other countries on our healthcare system. And the US life expectancy actually declined slightly over the last decade. To improve the health of the American people, I see two major challenges that NIH must respond to. First, many communities are underrepresented in research. Data is especially lacking for populations who are older, uninsured, belong to minority groups, or live in rural locations. You at NIEHS know this all too well because these communities are those that are critical to your work to understand the influence of environment on health. Second, research knowledge is not being effectively harnessed. Fundamentally, for all the wealth of data that we are able to collect, we still lack sufficient information to guide everyday clinical care. Among my guiding principles as director of NIH, the very first one is that our work is not finished when we deliver scientific discoveries. Our work is only finished when all people are living long and healthy lives. Fundamental science is the foundation of what NIH does. We're learning so much through basic research in our laboratories and out in the field. As this rush of information comes in, we must become more effective in connecting what we learn, understanding the interplay between the genes we inherit and the environmental and societal factors that surround us, beginning even before birth, and connecting that knowledge to everyday life and clinical practice. Whenever possible, we need to move as quickly as we can from biological insights to improvements in the lives of real people. NIH research encompasses the laboratory, the clinic, and all communities. The public must be our partners in discovery. My hope for NIH is that in the coming years, we will better connect research to efforts that have real-world impact. For example, I hope that we can deliver truly evidence-based healthcare by integrating all forms of relevant data and by giving patients across the country the option to participate in clinical research. NIH can also help make advanced scientific methods, such as new data analytics, more widely available to help deliver data-driven healthcare. Artificial intelligence is already revolutionizing what is possible for biomedical research and clinical care. However, to realize its potential for improving health, we need to invest in a secure and sustainable data sharing infrastructure and be sure to include data that represents the true diversity of our nation. In short, my goal as NIH director is to work toward making sure that our fundamental research engine is vital, delivering new insights and much needed technological advances, and also that everyone has access to evidence-based treatments and the opportunity to participate in and benefit from behavioral and biomedical research. Toward that end, we've just launched a new pilot program to better connect research to primary care. It's called Communities Advancing Research Equity, or CARE for Health. The program will soon announce its first grants, which will focus on engaging communities in areas that are underrepresented in research, with the first grants to be awarded in rural communities. I encourage all of you to think about which of your research questions might be addressed by connecting with primary care practices in very diverse communities. NIEHS has long emphasized community-engaged research and advancing health equity, and this long-standing commitment, as you can see, resonates deeply with my priorities as NIH director. I congratulate Dr. Rick Wojcik and all of you who helped to prepare the new NIEHS strategic plan, which I had the opportunity to read recently. It is very forward-thinking and very timely, and also so well aligned with our hopes for NIH overall and our desire to see more collaboration among the NIH institutes and centers. The environment has impacts on every organ system and every stage of life. It plays a part in both chronic and acute diseases, and we must bring awareness of environmental impacts to all areas of health research across NIH. We not only inform healthcare, we inform public policy that can change the impact of human activities on our environment. Just as mapping the human genome revealed new research paths across all NIH institutes, a greater understanding of the exposome and integrating data with and from exposome studies could well be the next step forward for precision approaches to preventing and treating diseases and making impactful public health interventions. Given the profound impacts of the environment on human health and disease, it is so important that NIEHS continue its work to build the tools and lead the science that will allow researchers across all NIH institutes and around the country to explore the importance of the exposome and the overall environment to human health. I really appreciate the opportunity to speak with you today. Sorry that because of my official travels, I'm not able to attend in person and engage in a discussion with all of you, but I wish you all a most productive meeting. Thank you.
Well, just the comment that I'll make is that as I warned you in my introductory remarks, she's very much very excited about the work that we do at NIEHS, is very interested in making sure that the work we do integrates with the studies that are happening across the NIH and across the biomedical spectrum. So she's been very supportive, and it's just been truly a pleasure working with her. So at some point, we're hoping that we will get, well, I know that she will be coming to NIEHS when she can fit this into her schedule. So David, where do we stand? I think we're running a little bit ahead of schedule now.
We are running a little bit ahead of schedule. My camera's okay. There goes my camera. We are a little bit ahead of schedule, and we do not have Eric Green on yet because he hasn't scheduled to speak until 10. So I'm wondering if we want to maybe take a little break and see if he is able to join early, or see if Lisa Ryder may be able to join and we can swap the order of presentations.
David, why don't we let's just take a break instead of swapping out the orders on things. So let's take a break. I think if everyone could be back at 5 minutes to 10, back at our Zooms, and then we'll be ready to go when Eric starts his lecture at 10 o'clock.
All right, that works for me.
Thanks, everyone.
So we'll resume it at 5 until 10. Thanks. Bye.
Okay, well, welcome back, everyone. Before we move into Dr. Green's presentation, I want to take a minute to remind everyone that today, September 11th, is the 23rd anniversary of the terrible events that marked the horrific attacks on the United States. So I'd like to take just a few minutes to read parts of a statement that President Biden issued to all Americans. So it goes as follows. Today, we honor the brave Americans who met the terror of September 11th with extraordinary acts of courage and sacrifice. In our darkest hour, when terrorists believed they could bring our country to its knees, those Americans proved that our nation's unbreakable spirit would prevail. In the moments, days, and years after the attacks of September 11th, heroes were forged. Firefighters, police officers, and first responders ran into the inferno of jet fuel and debris at Ground Zero, risking their lives to save the lives of others. Service members and civilians rushed into the fiery breach at the Pentagon again and again to rescue their colleagues. The patriotic passengers of Flight 93 made the ultimate sacrifice to prevent their plane from being used to take more innocent souls. And in big cities, rural towns, suburbs, and tribal communities, hundreds of thousands of Americans' hands went up, ready to serve our nation in uniform. So we owe these patriots of the 9/11 generation a debt of gratitude that we can never fully repay. So I just want to take a moment of silence, let's take a minute here in memory of all those that lost their lives 23 years ago on September 11th, 2001. Okay. Well, let's move on. And I will say it is with great pleasure that I can introduce my colleague and friend, Dr. Eric Green, who's the director of the National Human Genome Research Institute, NHGRI. So Dr. Green finished his MD PhD from Washington University, and almost immediately, in fact, during his PhD work, he became intimately connected with the Human Genome Project. He was the founding director of the NIH Intramural Sequencing Center, then moved up to be the chief of the NHGRI Genome Technology Branch, and then moved into the role as the scientific director at NHGRI prior to becoming the director of the Institute back in 2009. So he has authored or co-authored over 390 scientific publications, and he has characterized several human disease genes involved in hereditary deafness, vascular disease, and peripheral neuropathy. So he's received numerous awards. I don't have time to go into all of them, but most notably, he was elected to the National Academy of Medicine back in, well, last year in 2023. So it's truly been a pleasure working with him, most notably in our collective efforts to better understand the gene by environment factors that can be influencing human health and well-being. And I have to say, I've also admired his leadership over the past several years to weave genetics and genomics into the fabric of how we all study the etiology of human disease. And as you will hear tomorrow, when I give my presentation on our strategic plan, I'm following his lead on this strategy to better integrate environmental exposures into studying the human health and disease. So Eric, without further ado, let me turn the virtual podium over to you, and thank you so much for joining us today.
Well, thank you, Rick. It is certainly a pleasure to be here. I'm delighted to share some exciting things that are going on in genomics, a field I've been intimately involved with essentially since my entire professional career. By way of background, I'm trained as a physician scientist, as you heard. I got involved in genomics essentially at the beginning of the field. As an MD PhD, I was particularly interested in thinking about health applications of genomics, but the Human Genome Project took a significant fraction of the first part of my career. 30 years ago, I came to NIH, and then, as you heard, I've had various leadership positions, but just shy of 15 years ago, I became the NHGRI director right at a time where genomics was really in an opportune position to start to think about medical applications of genomics. Now, NHGRI has a very broad scientific portfolio, both intramural and extramural, everything from very basic technology and genome structure function to using genomics to identify the causative genes of many human ailments, to clinical applications, as well as ethical, legal, social implications research, et cetera, et cetera. I don't have time to describe all of that. And thinking about what to talk to you about today, I thought I would really emphasize the opportunities to make genomic medicine a reality and to tell that story, giving a passing highlights about things in other parts of our portfolio. During the Q&A, I'm happy to answer about anything going on at NHGRI. So let me just start with a teeny bit of history and just point out that there were really two scientific interrelated fields that were launched last century that I would contend are changing medicine this century. By way of history, you may not know that it was in 1907 that the word genetics was coined and was first appeared in the scientific literature. Genetics, of course, is the study of inheritance. At the time the word genetics was coined, there was really no knowledge yet about what was the molecule of heredity. Shortly thereafter, it was eventually discovered what it was, and the pivotal discovery about DNA as the hereditary material, of course, was elucidating its fundamental double helical structure that happened at about the halfway point of last century. A number of developments that took place throughout the 1950s, the 1960s, the 1970s, into the 1980s led to the arrival on the scene of an increasingly powerful set of tools for studying the structure of DNA, including molecular cloning, DNA sequencing, polymerase chain reaction, and others. And this all catalytically led to the idea of beginning to think about how to tackle the complete characterization of all the DNA of an organism, which of course is called its genome. And that led to the creation of the field and the coining of the word genomics in 1987. And of course, the reason why genomics was getting a lot of attention and a word was created and a field was launched in the late 1980s was by then there was already a coming together of an idea of launching a major project to once and for all read out the blueprint of humans and a series of other organisms. This, of course, got to be known as the Human Genome Project, a project I got involved in literally as a postdoctoral fellow, as a resident in pathology. I was in the right place at the right time and felt very fortunate to be able to start my career, in essence, it hijacked my career, as being able to be a participant on the front line of the Human Genome Project starting on October 1 of 1990. Now, many of you, I'm sure, are familiar with the Genome Project. If you weren't around during it and watched it, I'm sure you've read about it, heard about it, because of its seismic impact. By any criteria that you want to use, the Human Genome Project was wildly successful. It ended in 2003, accomplishing all of its goals, including its signature goal of generating the first sequence of a human genome. Now, we are certainly have seen ourselves made incredible progress over the last 21 years, including our desire to regularly commemorate key anniversaries. And certainly last year in 2023, we had a lot of commemoration going on and a little bit of thinking back on the first 20 years of having the human genome sequence in front of us and really thinking about what has changed since the end of the Human Genome Project. But what I want to do in this talk is to now tell you about one of the key rationales for the Human Genome Project, which is really what brought the NIH into it, because it was multiple funders, including the Department of Energy in the United States and other funders around the world, and they came in with different reasons for participating in the Human Genome Project. But the reason the National Institutes of Health was brought into being really pretty much the lead funder for the Human Genome Project was the recognition that improving human health was always a key rationale for the Human Genome Project. And the rationale behind that was the fact that so much of what I learned about in medicine, and it's almost still most of what we teach in medicine, is really based on the average patient. But we know that each patient is not average. Each of us is unique, and knowledge of the specific features of each person's uniqueness, whether it be their physical and social environment, which NAEHS is thinking a lot about, or the other part of that equation of our uniqueness relates to our blueprint. And if we, in the case of genomics and the genomic blueprint, the rationale for the Human Genome Project was we had the technologies at that time, perhaps, to figure out what the human blueprint was, and then be able to develop the means to study individual patients' genomes as part of their medical care. And so way long ago, when I got enamored by genomics and got involved in the Human Genome Project, was because I saw the potential of someday genomics becoming relevant to medicine. It should therefore come as no surprise that when the Genome Project ended, whether it was the popular press like the New York Times magazine or the scientific press like Science magazine, they put the words together, genomics and medicine, leading to the phrase genomic medicine. Now, this was exactly what we needed to start thinking about when the Human Genome Project had ended. There was only one problem, is that while we could spell genomic medicine, it was a very blurry concept. We needed to bring it into focus. And this became a high priority for NHGRI, my institute, having basically accomplished the goals of the Human Genome Project and checking the box that said why we were created by the US Congress, and we didn't really think it was valuable to shut us down, having accomplished the Human Genome Project. We needed to figure out what we needed to do next, and it was very clear that that destination for our institute was going to be making genomic medicine a reality. Now, it was a blurry concept, and we could start to define it at the time, and we started to regard this as eventually going to be a medical discipline that would involve using genomic information about an individual as part of their clinical care and other implications of that care. And that is a laser focus on genomic information. Now, there are other related terms that are frequently used: personalized medicine, individualized medicine, most recently precision medicine. I think these are terms that really marry together our two institutes, because those terms account for both genomic information as well as other information about people's lives, their physical and social environments. And those are the broader framing of personalized, individualized precision medicine. I will use the more narrow framing of genomic medicine, just thinking about the genomic information about each patient, not disrespecting the other parts, but just knowing that that's the area of expertise. And what our mission is related to is the genomic side of that equation. So what really happened, it was 21 years ago, we started a pivot. The Human Genome Project was the first journey of human genomics, and now we were ready to start a new journey. And the new journey required a pivot where we had a new starting line. It was the end of the Human Genome Project. And then we had a new destination, which was realizing genomic medicine, however blurry that concept was. Well, we had just finished the Human Genome Project, and we knew that these audacious journeys require multiple steps. And when you start the journey, you don't even know what all the steps are. But what you do is you just take the steps one at a time. By the way, believe me, we had no idea how we were going to map and sequence the human genome when we started the Human Genome Project. It was absolutely a build the airplane as we flight it. It was terrifying. We just figured out what we needed to do next and just kept marching along until we figured it all out. The gratifying things about these journeys is as you complete the steps, you get to cross them off your list. You go check, 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 and then eventually you inch your way closer to your destination. And the other thing I would immediately point out about this even more complicated journey of realizing genomic medicine compared to the journey of the Human Genome Project was we knew this was going to take a long time, many more years than the Human Genome Project. We knew it was not going to be accomplished by one scientist, by one institution. It was not going to even be completed by one part of the NIH or even one funding agency or even one country, nor was it going to be completed by one discipline. And I think the better analogy to this journey is of a marathon. And we are still in the midst of that marathon, running shoulder to shoulder with many people, many disciplines, many scientists and clinicians and healthcare professionals around the world. But it is an amazingly exciting marathon. So what has happened since the pivot? Okay, and the pivot really began once we had accomplished the signature goal of the Human Genome Project of sequencing that first human genome. Well, I'm going to now give you an instant replay of 21 years of progress in probably less than 2 minutes that represents an amazing amount of work done by our institute and others around the world that have led to some signature steps in that journey towards realizing genomic medicine. Because we could check the first one off, but then when the Genome Project ended 21 years ago, the very first thing we said was, whoa, we were successful, but that first human genome sequence, that cost us $1 billion. And so we stimulated through technology development grants and the private sector got involved. And we recognized that reducing the cost of sequencing a human genome was the very important next step that needed to be done. And we have now successfully reduced the cost of sequencing a human genome by more than 1 million-fold. It no longer costs $1 million. In fact, it now costs less than $1,000. And in fact, it was the $1,000 genome that was sort of the mantra for that effort. And it was deliberately picked as $1,000 because that's a very reasonable clinical test. Well, we have cheap sequencing. We weren't going to stop with one human genome. And we have now gone on and sequenced millions of human genomes around the world. We have cataloged the differences that exist in our genomes. Any two members of the NAEHS Council, your genomes are 99.6% identical to each other, but we're very interested in those 0.4 differences that exist across any two people's genomes. And we have now developed rich catalogs of those variants because we've now have sequenced many genomes. We need to sequence a lot more genomes, but we have made major strides in understanding the repertoire of genomic variation that exists across human populations. And with that, we have learned and increasingly learned a tremendous amount about the role that variation plays in influencing genome function. But of course, to do that, we had to go and work incredibly hard over the last 21 years to actually understand how the human genome works. I often say that I often point out that the Human Genome Project just laid out the 3 billion letters of the human genome. It was not about delivering an interpretation. We knew that would take generations and generations. In the first 21 years, we've done a pretty good job. I won't give it a big check mark. I'll give it a medium-sized check mark because my children and my grandchildren will still be interpreting and reinterpreting the human genome. But wow, have we learned a lot about over the last 21 years? We have a pretty good catalog of our 20,000 genes. We have an incredibly high appreciation of the complexity of our non-coding portions of the genome. We know a lot more about RNA now. We know a lot more about regulatory elements and transcription factor binding sites, et cetera, et cetera. But it is a complicated 3 billion letters. We've got a lot more to learn. We continue to be invested heavily in understanding the complete functional characterization of the human genome. With cheap tools for sequencing, better understanding of genomic variation, better understanding of genome function, we have empowered scientists around the world to take these genomic resources and these genomic tools and really make significant advances in unraveling the genomic bases of human disease. The human disease story is a complicated one with often an interplay of genetics and environmental and social influences. The easiest ones to understand are rare diseases, which are caused by defects in single genes. There's about 10,000 rare diseases. We have gone from knowing only about a few dozen rare diseases, what the gene causes, what the gene is that's mutated in those diseases when the Genome Project started. We're now about 6,000. That's incredible progress. We have now made tremendous strides in understanding through genome-wide association studies the literally hundreds of thousands of regions in the human genome that contain variants that confer risk for human more common genetic diseases. Those are ones that have multiple genetic influences and what are often a greater influence of the environment. But we don't know we don't know nearly any of those variants, which are the causative ones, how they confer risk. But we have set up a circumstance where interrogation of those associated regions are now going on at very large scale to try to see if we can decipher the genomic basis of human disease. We've made great advances, but it only gets a medium check mark because we have so much more to go. Finish out the list of all the rare genetic diseases and their associated genes, but also more importantly, figure out these incredibly complicated common diseases where multiple genomic influences, along with physical and social environmental influences, are conferring risk for disease. That's my more basic and translational side of the story, but it's actually not what I want to tell you about in detail. What I want to tell you about in detail is what's really transpired over the last, I don't know, maybe 6 to 8 years. Because by the middle of last decade, things really started to settle into place with respect to efforts to apply genomics in medicine. We had cheap genome sequencing, catalogs of genomic variants, functional understanding of the human genome, and we had this great progress in disease gene identification. Every week would come out stories of a new disease, almost always a rare disease, for which we figured out these genes and these diseases. Now, these developments then culminated with some of the earliest examples of truly having genomic medicine being implemented. And while these initial examples I'm going to tell you about are really just the tip of the iceberg, they've been incredibly informative to teaching us what this is going to look like going forward. Now, why is it that we've gotten to the point where we can actually now use genomics in medicine? And there's really two oversimplified reasons. First of all, we've just gotten to the point where we can analyze a patient's genome because it's become cheap. And as a result of it becoming cheap, we can generate that data. And then second of all, we are getting better and better of then using that sequence to actually figure out what variants the patient has. And typically each of us have something like 3 to 5 million single letter differences. And we determine that by comparing that cheap sequence we get from a patient, and we compare it to a reference, a gold standard. I'm going to tell you more about references later. And from that, we're able to get a list of the genomic variants, about 3 to 5 million. And from that, we could do all sorts of analyses and implement genomic medicine. That has led to a situation where genomic medicine is here and now. We're beginning to see real implementation. Before I give you specific examples, I do want to point out to you that there has not been a particularly logical way that these examples have popped up. Unlike the story of the Human Genome Project, was very logical how we went step by step. It was really interesting to watch where genomics found its way into medicine. And rather than being a grand unifying plan, there were just sort of opportunistic situations with different clinical niches that emerged, each with an acute diagnostic need, and in some cases, a technological capability, and sometimes it even related to things like insurance, whether it would get paid for. So let me tell you about what are the 5 substantive areas that I believe, as the NHGRI director, truly reflect genomic medicine being implemented. The first is probably, in some ways, an incredibly big one, and that relates to cancer. We have a whole institute at NIH, and I'm going to show you like 3 slides, but I'm sure you could get dozens of people from the National Cancer Institute because they have completely embraced genomics, recognizing that genomics is a disease of the genome. It's about cells picking up changes in their DNA that make those cells become malignant. And what has happened over time is that we have now found ourselves in a situation where we can augment the skills of a trained pathologist who looks at histopathology and says, oh, yeah, that tumor, it looks like this, it looks like this. So based on knowing what that tumor looks like, we know what we might recommend as pathologists. But we're augmenting that because now that tumor from that patient will get their genome sequence in many cases. And from that, you will get a fingerprint of the derangements that have been picked up in that tumor, in that patient, and that gives unique information. And importantly, it augments the morphological information and adds to it another individualized, more precise set of information about that particular genome in that particular tumor. And this is actually leading to all sorts of interesting things, including a paradigm change that the genomic signatures of a tumor often and perhaps almost always provide more valuable clinical information than the tissue of origin. So more and more, you're hearing stories about where decisions are being made, not based on what part of the body the tumor was taken out of, but what that genomic signature looks like. There are other ways in which genomics is having a major influence in cancer, and that has to do with the ability to detect cell-free DNA that floats around in our bodies naturally. And if we happen to have any cancer in our bodies, the cancer cells are turning over and spilling out cell-free DNA. And instead of having to do a physical biopsy, increasingly people, rather than using standard biopsies that could be invasive and dangerous, people are increasingly relying on the fact that if a tumor is in our body somewhere and it's going to be dying, there's going to release DNA in the bloodstream. And these highly sensitive new DNA sequencing methods can also just detect and analyze that cell-free DNA through a simple blood draw. And that is what is known as a liquid biopsy. This is being applied for surveillance, for early detection of otherwise healthy people. And I think we'll hear more and more about this in the future. It's also used for surveillance because you can detect cell-free DNA of a known tumor when it returns long before you will find it by more traditional radiographic methods. And so this is just another example where in certain clinical settings in cancer care, even liquid biopsies are becoming relevant. Now, I just couldn't help but I came across this article and I just wanted to share this with you because I thought it was, because this is a huge field, cancer genomics. By the way, our institute does almost no cancer genomics because all of it's being done now at the National Cancer Institute, which is a much larger institute that focuses exclusively on cancer. But last year they had this in retrospect because it had been 15 years earlier that you can see here that the first comprehensive sequence of a cancer genome was reported, and that ushered in its new era. And I just love this quote I wanted to share with you. It said, "Today, genomic sequencing as part of clinical care has transformed cancer diagnostics, clinical trials, and the use of new therapies to improve outcomes for people with cancer. Our unprecedented view of the cancer genome empowers clinicians and computational biologists and bench scientists alike to define biologically relevant groups of people with cancer, direct genomic inquiry, and ultimately identify new therapies and biomarkers." That's just overwhelming. In fact, I would contend that 20, 30, 40 years from now, the greatest impact of genomics in medicine will be in cancer. A second area that has become very exciting relates to rare genetic disease diagnostics. And here, the idea is quite straightforward, is that increasingly, when a patient appears that has a condition like developmental delay, especially a child, or heart abnormality, that increasingly, rather than doing big diagnostic workups, we'll just sequence their genome. It'll cost less than $1,000. And from that, we will, in many cases, be able to deliver a diagnosis as is illustrated in this figure. And to give you a really impressive progress here, there's a whole literature development. We've done lots of studies. I just happen to pick my colleagues at the Broad Institute who published something earlier this year where they looked at their history of looking at sequencing genomes as a frontline diagnostic tool for a patient with a genetic disease. And the bottom line is this and other studies are yielding diagnostic rates of 30 to 50%. In other words, you have a patient in front of you, you think they have a rare genetic disease, you sequence their genome 30 to 50%, you get the answer. That number will only get better as we understand the genome better and we understand genomic variation better. I think that's incredibly impressive. So that's in the routine case, but we've also seen situations where in the case of undiagnosed conditions where you really have no idea what's wrong with the patient. And in some cases, these patients have been on long diagnostic odysseys. Again, genome sequencing becomes a frontline tool. And there's in fact been major programs set up by NIH, both intramurally and extramurally, to tackle the complexities of undiagnosed diseases, often leading to the discovery of new diseases. And there's another niche, which I think is incredibly impressive and comes directly from studies that we launched, maybe about 10 years ago. And that is the recognition that if you encounter neonates in a neonatal intensive care unit, that neonatologists can't figure out what is wrong with that child and actually can often predict that that child might expire in the next few days. Our researchers that we supported were able to develop rapid genome sequencing, meaning like get a genome sequence in less than 24 hours with an interpretation. And it's amazing what has happened. More and more neonatal intensive care units around the world are adopting this rapid genome sequencing diagnostic method because it saves lives. A review that came out earlier this year, by the way, the UK in particular, has been really leading in many ways in genomic medicine. And this came out of some studies that they did. They actually reviewed 44 studies that had already been published looking at rapid genome sequencing in neonates. And let me just give you a quote from this. In 44 studies in children in ICUs with diseases of unknown etiology, 37% received a genetic diagnosis by rapid sequencing. 26% had consequent changes in management, and it saved the healthcare cost of an average of over $14,000 per child. So in 5 years, there is the potential for infant and childhood mortality in the US and UK to be reduced by several percent through the use of rapid genome sequencing as a first-tier standard of care test for children in ICUs with diagnoses of uncertain etiology. Genomics saves lives, and this is incredibly impressive how fast this has come about. A third area that's had a rapid uptake is at the other end of pregnancy. I was just telling you about newborns, but it turns out that we now have all new ways of doing prenatal genetic diagnoses. Now, prenatal diagnoses have been around for a long time. Traditionally, they were done through more invasive methods. Before genomics came around, we would do amniocentesis, get a little bit of amniotic fluid where there'd be fetal cells, look at the chromosomes, and define aneuploidy, like 3 copies of chromosome 21. Amniocenteses are hardly done anymore as a primary screening method because it turns out that, like with tumor cells, the placenta also turns over cells and releases fetal DNA into the bloodstream. And both mother and fetus contain cell-free DNA from these dying cells. But as an alternate to having to go and do amniocentesis, you could do a simple blood draw of a pregnant individual and look at the cell-free DNA. And from that, you could assess whether there's aneuploidy. Even though it's a mixture of maternal and fetal DNA, you can detect at a screening level whether there is aneuploidy or not. So as a screening method, this has now become the #1 genomic medicine test worldwide. It's estimated that upwards of 8 million pregnant individuals will have this non-invasive prenatal testing done this year. And it is remarkable that it has it's caught on. And part of the reason is because insurance pays for it now. And I know now of dozens of even staff members at my institute, young individuals who have become pregnant who are getting this non-invasive test as part of routine prenatal care. The fourth area is an area that is very exciting, although the uptake has been a little bit slower, and it relates to a big word, pharmacogenomics. Well, what is pharmacogenomics and what's pharmacogenomic testing? Well, people respond differently to everything, right? I mean, I'm the guy I'm the guy in the red shirt. I hate roller coasters, but some people love roller coasters. Well, the same thing how they respond to medications. Every medication you get at Walgreens or CVS, every one of them work. They wouldn't be sold by a pharmacy. They just don't work for everyone. And in fact, they don't work particularly well overall. There's been many studies, but shown here on the left these are 10 fairly commonly prescribed medications. And you could see that for every individual in blue where the medication works, or all the individuals in red where it doesn't work so well, either it makes them sicker, it doesn't work, has the wrong dosage, et cetera, et cetera. We could do better. And we've known this for a long time. We could figure out not how to design unique drugs for each person, but rather how to pick the right drug, the right hypertensive, the right asthma medication, the right medication to use for some mental illness. Bottom line is we could pick the right drug for the right person based on their genomics. And the basic idea is that many, not all, but many of the aspects of variation of people's responses to medication have to do with variants that exist in people's genomes that influence their drug metabolism pathways. And we're learning which genes those are. And we're learning which variations determine whether you're a good responder or a bad responder. So we're getting to the point where we can take the same patient group and look at their genome and based on their variants, figure out if they're going to be a good responder, a bad responder, need a higher medication, a lower medication, et cetera, et cetera. And so one size doesn't have to fit all. We can stratify patients before deciding which medication to give them. We get the right drug to the right patient at the right dose. Is this all hypothetical? Well, no, it's not. It's getting real. Shown here is a typical data, although it's actually old data. There's newer data coming out, where out of all the FDA-approved medications, 7% of them already are associated with what's called an actionable pharmacogene. In other words, a gene that has variations that influence how you respond to that medication. 7%. It's probably more like double that now. But out of that 7%, it accounts for, at that time when this analysis was done, almost a fifth of all prescription medications given, all prescriptions given out. And this is why companies, and I'm not endorsing this company, I'm just giving you an example. This is one of the diagnostic companies that offers lots and lots and lots of tests for pharmacogenes for specific medications. And these are, pretty commonly used medications. I give you an example of some drugs and what they're used for. And in many ways, if you get any one of those drugs, there's a very good indication you should first be pharmacogenomic tested to figure out if the drug's right for you or whether we need to adjust your dosage and so forth. The uptake has been slower than we anticipated. I think pharmacogenomic testing is now appropriate for a small subset of prescription medication. We think it's going to grow in the future. A lot of this has to do with getting insurance companies to pay, getting clinicians to understand it, getting clinical decision support tools put into electronic medical records and so forth. I would just urge you to watch this field. I think it'll continue to grow in the coming years ahead of us. The last area I would say that I want to share with you, number 5, is related to prevention. Because here, I think there's some really exciting things and then some things to look for. Exciting because they're here and now, things to look for because they're active research. Most of what I've been telling you about for genomic medicine has to do with dealing with medical situations, but prevention is an important upstream circumstance relative to medical care. And prevention is absolutely becoming relevant for genomics, especially for rare diseases. I could give you many examples. Probably one of the best examples has to do with something like predisposition to colon cancer. And individuals who have a family history, we might test that gentleman because he has a brother who had colon cancer, and we might find, because we know where to look, some of the most common variants that might confer risk for that individual to get colon cancer. And from that, he may get more frequent colonoscopies, will catch his cancer earlier, and that will save lives. Similarly, for a girl like this, we may find out because of newborn screening or because of a sibling or another relative that she has a genetic defect and needs an adjusted diet. Without the adjusted diet early in life, she may develop cognitive delay. But through that prevention, that genomic testing early in life, we could find out that she does have those variants and she should have an adjusted diet, and we will prevent her from developing cognitive disorders. And so prevention is absolutely becoming mainstream for rare diseases, and they're here and now. In the case of common diseases, we don't know enough about the specific variants that are causing risk for common diseases, but through something that many of you may have heard about called polygenic risk scores, we can profile people for their full repertoire of variants, and we can compare their variants to other people's variants that we've learned about, such as what the distribution looks like for developing diabetes or for maybe sudden cardiac death or sudden seizures. And we could bin you into a distribution that may tell you, based on your polygenic risk score, whether you're at a high risk or a low risk for a disorder that may be preventable. And from that, maybe we could monitor you more carefully or do things to sort of mitigate having that disease affect you in a serious way. This is very exciting, but this is not ready for prime time quite yet, even though some companies are trying to market it as such. This is an active area of research. We fund a lot of research about polygenic risk scores. Other institutes are doing it. I would encourage you to follow this because I do believe in the next 10 years, we might see some exciting developments in polygenic risk scores that might be very applicable for some very common diseases that are very relevant, and it might become part of the preventative milieu of our medical system. So those are the examples I wanted to give you, and I would just say to finish out this En Route to Genomic Medicine highlight reel, we have now vivid examples of genomic medicine now emerging. But I'm only going to give this a small check mark because that check mark is just the earliest examples. And I think we have certainly a long way to go before we're going to fully fill out that repertoire of these disorders. But I wanted to point out to you, and I wanted to now tell you a little bit about some of the bigger challenges that we're now facing in this field. Because this, all these successes in genomics have not been a linear path. The journey is something that looks much more like this. That's what research is all about. And we do face some pretty big challenges. And I wanted to make sure to balance this optimistic first part of my talk with some real challenges in the second part of my talk. And what I want to specifically focus on is saying, because you're probably hearing about this more and more, is that analyzing a patient's genome sequence is not simple. It is quite challenging, and I want to own those challenges, but NHGRI is trying to adjust those challenges. I mean, we could take any patient in any hospital, and we could sequence their genome. We could even do it in 24 hours if we needed to. And we could figure out the 3 to 5 million variants that they contain, single letter variants. But when we round on that patient in the morning, the fact of the matter is most of those variants, we have no idea what they mean. And I slightly misled you because earlier in my talk, because I showed you this slide and made it seem that it was simple. It was an oversimplification. And I want to explain to you, because I think it's very important for people to appreciate why this is still a very challenging area and what NHGRI is trying to deal with it. Let me point out that there are 3 major steps associated with analyzing a person's genome. You got to detect the variants, you got to figure out which ones are possibly relevant, and then you got to figure out how they're relevant. Let me tell you about each of these steps, and I'm going to give you a little education about how we sequence genomes now. So first, you got to detect all the genomic variants in a person's genome. In order to do that, you need to have something called a reference sequence. And so what is a reference sequence? Well, a reference sequence is sort of a gold standard. It is saying you want to compare it to. It has to be super high quality. It has to be meticulously generated. This is what the Genome Project did. And it requires multiple technologies to make it really perfect. And it has to be virtually complete, no or very little missing sequence. Today, we are generating reference sequences for about $10,000. They are not the diagnostic $1,000 genome. It's still an expensive thing to do, but it's a lot less than the $1 billion, the first one we generated. When a patient gets, or a research participant gets their genome sequenced, they get a routine genome sequence. A routine genome sequence, its goal is not to be meticulous and perfect. Its goal is to identify genomic variants. It's generated in a very high throughput way using a single DNA sequencing technology in a very high throughput fashion, and it always has missing sequence. But it's for diagnostic purposes, but it's also cheap. It's less than $1,000. Well, how do you do it? How do you generate a sequence so cheap that allows it to be used diagnostically? Well, we do this by taking a patient's DNA, we fragment it, and then we feed it through a sequencing instrument like an Illumina instrument. I'm not going to go into what's in the black box, but we generate a bazillion sequence reads. We do not stitch together those sequence reads in isolation. What we have to do is we need to use an existing reference sequence to help us figure out what that patient's sequence is. So we take an existing reference sequence like the one that the Genome Project produced or one that's been refined since then, and then we go one read at a time, and we simply say, okay, where does that read match in the reference sequence? And we find out where that read matches, and we assign it, okay? And now we can take that and we say, okay, this patient's, it goes on this particular part relative to the reference sequence. And then we keep doing this across all these generated other additional reads. And we therefore are able to put into place each of the sequence reads all relative to the reference sequence. And so watch this go through. It's just going to fill in, fill in, fill in. It is not a de novo generation of the patient's genome sequence in and of itself, but rather it is done in a fashion that allows each and every read to first be matched to the reference genome and then eventually find its way over. But occasionally, a read may not match the reference sequence, and it sort of goes into a non-match category. This is going to be very important for reasons I'm going to describe to you in a bit. But we keep doing this, and it goes over and over and over and over, and eventually we are able to fill in not all, but most of a genome sequence, but good enough that it costs less than $1,000. It's diagnostic grade, it is routine, and this is what is done for less than $1,000. But it does leave a few reads typically on the floor, if you will, or in a trash bin. But then what do we do with that generated sequence? We take that generated sequence where every single line of the genome sequence has been read many, many times, typically 30 times or more, to ensure that when we find a matching sequence, it is very high accuracy. And then we go through and we compare them. We compare that reference sequence to that reference-assisted generated routine sequence. And from that, we compare the sequences to find differences. And those differences are highlighted here. There's some single nucleotide, there's deletions, there's insertions, all sorts of differences, just looking for comparing yellow versus red. And from that, we generate a report. And that's the report that's given to a clinician or to the researcher when we generated one of these routine sequences. But here's what's important, and I really want to make sure it's very clear. That reference sequence came from one person, and or from a small number of people. But of course, that's not adequate because we need to have reference sequences that reflect the different ancestral groups because they're going to have slight differences in their genomes. Now, why do we care about slight differences in the reference genomes? Let me illustrate to you why that becomes so important. Because it becomes so important because when you do reference-assisted genome sequence generation, it means that as you take each one and you put those reads across it to generate the genome, you do it, but you get differing numbers of non-matching sequences. And of course, if you have a wrong reference relative to the person who you're sequencing, you're going to end up with a poor quality sequence with more holes in it because, as you can see from reference number 5 here, a lot of non-matching sequences because that person was too ancestrally diverged from the individual whose genome you were sequencing. So this becomes an equity issue because if you don't have the right reference, for example, references 5 or 7 for the patient, it's not good. It's not as high a quality, whereas something like reference 6 or reference 1 would be a more appropriate one for this individual. Many of you are probably hearing about something called the Human Pangenome Reference. And what this is putting together a series of references that we're generating and using those as a tool because they're better than just generating one reference sequence. So when you hear pangenome, it's a composite of multiple human reference genome sequences that captures the breadth of human genomic variation much better than any one human reference sequence and enables a more accurate and complete detection of genomic variants across diverse populations. And you use it in the same way. And this is an active area of research where these pangenomes are being put together and you use it. And from it, because you have more representation of the world's population, you have many fewer non-matching non-matching reads. So just to hit home the point, if you use a single reference, it's not going to be as perfect as when you would use a pangenome. Many fewer matching sequences, more complete genome sequences, more detection. So you get, compared to a single reference, fewer true variants, more false positive variants. A pangenome is going to improve this on all counts. And that is why NHGRI has this major program called the Human Genome Reference Program that is building pangenomes, building reference sequences from diverse representatives of the human population. So that allowed us to detect the variants, but we similarly have to deal with, in the case especially something like for rare genetic diseases, figuring out which of those variants are relevant. In order to do that, you need to filter them. And what's important to recognize in the case of rare genetic disease diagnostics is that the vast majority of genomic variants that are causative for rare disease, in other words, are pathogenic, they're rare. But being rare does not necessarily mean a genomic variant is pathogenic, but being common means it's likely not pathogenic. So think about that. It must be rare to be pathogenic, and so we can at least rule out the common ones in a filtering. And so what happens is we take this list of genomic variants and we filter them down, and we remove the common ones and more carefully prioritize the rare ones. And after filtering, we prioritize those rare variants as being possible candidates for being pathogenic. So to oversimplify the point, a given person typically has 3 to 5 million variants, and we have analysts who developing better and better tools for filtering and prioritizing to reduce the numbers down to 10,000, 1,000, and eventually get down to maybe 10 to 20 such variants that you want to then characterize. But here's another equity problem that we're dealing with, is because how do you figure out if something's rare? Well, you figure out if something's rare by comparing it to large collection of variants that have been generated by sequencing lots of people in a population. The problem is you need to have the right population. So this is what is involved in genome aggregation. And so here, if we take 4 different ancestral groups, I represented them by 4 fictitious colors to represent just different ancestral groups, you get different patterns. I mean, here's a variant that's very common in all populations. So in this case, it's not going to be considered or prioritized because it's common. It's almost for certain not causing a rare disease. This is a variant that's rare in all diseases. It would be rare in all populations. It would be a high priority for study because it is rare in all populations. But here's where we can get confused. Here's a variant that if we only look at aggregated variants from population number 1, the far left the orange population, you may think it's rare. It's not rare. So you'd be wasting your time and potentially giving a bad diagnosis to somebody in the orange population. And over here for variant 4, you may think incorrectly if you're just looking at the orange population that it's rare, and you'd waste your time because it turned out to be common. But you didn't look at that population. So the bottom line, and by the way, misdiagnoses have been happening because we don't have enough aggregated data from enough populations. And here I'm just showing you an increasing literature that is coming out now where we are seeing wrong diagnoses because people are not having access to aggregated variants from enough different ancestral populations. Again, that is why we are fixing this through our reference program and through other programs to generate large numbers of genome sequences from populations across the world. So then you get it down to filtered, you got maybe 10 to 30, and the last thing you need to do is establish the clinical relevance of those prioritized variants. And here, I'm very proud to talk about a program we launched a number of years ago that many institutes are now collaborating with us on. It's called ClinGen, or Clinical Genome Resource. The mission of it is to build and support an authoritative central resource that defines the clinical relevance of genes and variants for use in precision health and research. It involves getting people around the world to help us analyze the literature, involving thousands of experts, multiple countries, to basically curate this literature to figure out which variants are associated with which genes are causative for which disorders. And this is an incredibly valuable network that now gives us the 3 key things we need for improving and having equitable analyses of patients' genomes. We need appropriately matched reference genomes and pangenomes. We need to aggregate these across multiple populations, and we need to have a curated resource to tell us which of those variants are the ones that are of critical importance. I'm actually going to skip through a couple slides because I know I'm running out of time, because I wanted to end my talk by pointing out that in 2020, we put out a new strategic vision that really lays out many of the things I've talked about today, including some of these programs I've been highlighting near the end of my talk. And I would strongly urge you to look at the strategic vision because it certainly covers our entire portfolio of research activities, but in particular, including what I described to you in the genomic medicine implementation space. But I know Rick got very interested in our strategic vision because we did something we hadn't done in any of our previous strategic visions, in that we went through and we actually ended the strategic vision by making a series of bold predictions that we thought about and decided to put into print. And so at the very end of our strategic vision, we put into print this box. I'll show you box 5, which laid out 10 bold predictions that NHGRI said, well, let's be fun and audacious and sort of say, what might this look like 10 years after the publication of the strategic vision? But we didn't say much about it in the paper. And in fact, in the paragraph that we wrote, we just sort of referred to it by saying, but now more than ever, solutions to these problems seem to be within striking distance. So towards this end, and with the characteristic spirit of genomics audacity, we offer 10 bold predictions of what might be realized in human genomics by 2030. And we refer to box 5. And everybody loved these bold predictions. So I had my communications group prepare a video that brought the bold predictions a little more to life than what we said in the one sentence of our strategic vision. So let me share this video with you, which I know Rick really likes.
Genomics, which is the study of all DNA in an organism called the genome, is changing the way we practice medicine, how we manage and treat some previously incurable diseases, and our relationship with society at large. Since the 1950s, double helix and DNA have become household words, standing in for the historic discovery of the 4 chemicals that give us life, commonly abbreviated as A, C, G, and T. Genomics is at an age of innovation and invention like no other, all thanks to how strings of those 4 letters encode the information for creating and operating something as complicated as a human body. Springing forward from the success of the Human Genome Project, a massive reduction in the cost of sequencing a human genome, and the dawn of the CRISPR gene editing era, genomics is leading into an even more audacious future, a future that will define our collective lives for decades to come. But what could this future look like? Here is a summary of 10 bold and fantastical predictions made by experts at the National Human Genome Research Institute and the genomics community for the next decade of human genomics. While most are unlikely to be fully attained by 2030, achieving even one or more of these by that time would have lasting impact for science, medicine, and society. Prediction 1. Sequencing and analyzing a complete human genome will become commonplace for any research laboratory. Prediction 2. The role of every gene in the human genome will be known. Prediction 3. Environmental influences on our genome will be routinely used for making predictions about health and disease. Prediction 4. Genomics will no longer use social constructs such as race in human research studies. Prediction 5. Student projects involving the study of millions of people's genome sequences will be regularly featured at school science fairs. Prediction 6. Genomic testing will become commonplace in medicine, just like a standard blood test is used now. Prediction 7. It will be readily known if a given letter difference in a person's DNA is clinically important. Prediction 8. A person's complete genome sequence will be available on their smartphone in a user-friendly form. Prediction 9. Advances from human genomics will benefit all of society and not just a few. Prediction 10. Genomic discoveries and technologies will help cure more genetic diseases than ever before. How do we get there? The National Human Genome Research Institute is committed to leading research to make such predictions a reality. Learn more about the Institute's 2020 strategic vision for the future of human genomics by visiting genome.gov/2020SV. Dive deeply into a field that continues to transform medicine and will hopefully continue to bring curiosity, purpose, and compassion for people everywhere.
Well, thank you very much. I hope you enjoyed hearing about the Institute's 21-year pivot, where we've gone from the vaguest idea of what genomic medicine was going to be to now actually seeing it come in focus. And so with that, let me encourage you, if anybody interested, I have a monthly newsletter you're welcome to subscribe to, and I'm a very active presence on social media. I can leave this up for a couple seconds if people want to see that, and happy to take any questions.
Great. Okay. Well, Eric, terrific. Well, thank you, and thank you for sharing that video. It is, as you know, that is one of my favorite things. The issue around those bold predictions. Let me encourage my colleagues on the NAEHS Council to ask questions. Daryl, I see that your hand is up. Daryl Hood.
Oh, thank you very much, Mr. Director. Thank you very much for that. Wow, that I'm going to use that in my course, by the way. Some of these points that you just made. But looking further ahead with regard to those 10 points there, I'm just thinking that certainly knowing that genetic data is very, very susceptible to many of the algorithms and that clearly these large language learning models that are going to be nested in your, for an example, your pangenome program and several of the others, I would say at least 5. And so, you know, this thing about I don't want to say just race, but what are your thoughts on how are you going to, or how are these models and programs going to reconcile the underrepresentation of equity input into some of these models? You know, so not necessarily talking about race, right? And so, do you understand my question? Is that
I think I understand your question. I mean, there's many dimensions associated with it. I completely agree. The notion of race is going to, genomics is going to prove over and over again that how we need a whole new way of thinking about diversity that that is not exclusively linked to race by all means. I think this is also becoming very relevant in something that's getting a lot of attention at the NIH level related to population descriptors. You may be aware that the National Academies just did a report that was actually commissioned. Actually, the NIH, my deputy director is the one that played a major role in helping coordinate the leadership of that across the NIH. Many institutes were involved, and there's lots of follow-up. It's given us lots to think about and talk about. But I particularly told the story of the challenges. If you notice, you might, some people think, oh, pangenome, that's a really interesting scientific challenge, and it is, but it actually is an equity story. I mean, to me, the biggest, what I really hope came across was the reason we're doing these incredibly sophisticated genomic, pangenome, reference genomes. It all has to do with the clear need to do this if we're going to provide equitable access to accurate genomic testing. And it just has to do with all of these issues of reference genomes and an overwhelming domination of European individuals of European ancestry having their genomes analyzed initially. And we've got to fix that. And we're in the middle of fixing that. And that's the reason we're doing it.
Great, because looking at it longitudinally, clearly, not to do so in terms of considerations for guardrails and sort of coming up with how we're going to reconcile this equity input right up front. That's going to lead to, in your genomic medicine paradigm, disproportional drug development and so forth and so on. Thank you very much.
Couldn't agree with you more.
All right, thank you.
Trevor, I see that your hand is up. Do you want to go next with your question?
I can, Rick. Thank you very much. Eric, terrific presentation and obviously a major success story. I wonder if you could just comment briefly on how do you think, because as you know, DNA organized in cells is chromatin and it's subject to a number of epigenetic modifications. So I wonder if you could comment on how you think that might contribute and maybe address some of the missing information that's there.
Yeah, no, I candidly admit at the beginning, and I'll absolutely admit now, I really I undersold the more basic side of all of this story, and I don't mean to imply for a second that just the variation in our sequence is the consequential thing we should be thinking exclusively about. And the great news, Trevor, and as you know, is that these DNA sequencing methods, all the new ones that have come out, are now readily adaptable to studying the epigenomic language of DNA. And with that is coming all sorts of studies, many of which are of great joint interest between our institutes, that is now looking at the epigenomic changes that take place in different diseases. And it's incredibly exciting. And then even separate from that is the whole RNA world, and now modifications of RNA, another thing we're doing jointly with NAEHS. So yes, there's that whole other story, which is why I refuse to give a big check mark to the functional characterization of the human genome. We got a long way to go, you know, and in my longer or my slightly different talk, I unpack that, where I unpack that more about all the things about human genome function we still need to learn.
Yeah, but terrific, and again, congratulations on what you guys have done.
Terrific, great. Dr. Hoyo, you have a question or comment? Catherine?
Yes. I don't know what. Okay.
We gotta get your camera on there. There you are. Good to see you.
Okay. Yes. Yes, this was a terrific presentation. My question has to do with the computational space, because it seems like on the sequencing side, you seem to have really made some inroads, but I'm not seeing a similar investment on the computational space side of things, because we're talking about huge data here.
So, so again, I probably didn't give enough. Nothing about my talk reflects budgetary distribution. I can tell you, we are investing hugely in data science. In fact, just over the last 2 years, I've created as a part of the institute called the Office of Genomic Data Science. We are overwhelmingly at the table at the corporate NIH level, dealing with all things data science. And you know, some days I'm incredibly proud of genomics because we became the poster child of why data science is so relevant in medicine. And then on other days, I feel guilty because I feel like if genomics had been a little more sleepy, we probably wouldn't be as stressed out as we are about data science right now. It's not the only big data that's out there in medicine, electronic health records, imaging data, and so forth. But you know, we're a big cause of it, and I can warn you, it ain't going to slow down the amount of genomic data that's going to be generated. So this is not going to be solved by the NHGRI and its 1.4% of the NIH budget. This is, and mostly because, you know, everybody's using genomic data. Rick and I and many other NIH leaders are working hard at bringing NIH up where it needs to be in the data science arena for genomic data, but for all these other types of data as well. And you're seeing this in Common Fund initiatives. You're seeing this in AI and machine learning projects. We have a new wonderful leader of our Center for Information Technology, Sean Mooney. We're going to have a new National Library of Medicine director probably on the scene in the next 6 months. It's getting a lot of attention, but I don't think it could get too much attention. It is actually probably what keeps me up at night as much as anything else. I want to see data science catch up with this surge of the ability to generate the data.
Great response, Eric. Gary Miller.
Let's say with that, thank you. I would say with that, maybe the personnel also are lagging behind. We are not training enough.
Agree with you. We're looking at that at the NIH level. And of course, the other challenge with the personnel is the universities are starting to train more, but they're getting more competitive. You know, we got to think about pay scale too. Yeah. NIH actually has adapted that even for we can hire more and more computational scientists at more competitive salaries because of some recent things we were able to convince the personnel system to allow us to do.
Great answer, Eric. Gary Miller, I see that you have your hand up.
Yeah. So speaking of data, I think one of the opportunities I see is you talk about this idea of integrating the environmental piece into it, because ultimately G by E is going to explain it. That's why so much of today's talks are about that. But one of my concerns is how we're developing infrastructures like on the genomic side, and people are doing it for proteomics. And as we develop exposomics, they're just all in parallel. and how are we going to get these groups that are working at different institutes and even agencies to come together in that data infrastructure?
Completely agree with that concern. I do think there's some, again, it's a great point. I think it's a point that is getting some attention. I will point out that we just launched a year ago as a first step, a new clinical program called Multi-Omics of Disease, where we at least are forcing people who are generating different types of omics data to figure out how to integrate these and do it not in siloed fashions, but doing it all within the same context. And I certainly think the All of Us program is setting up a situation where I think they can stimulate bringing in environmental and other data. And I know Rick is very active in discussions with all of us. But I agree with your sentiment, and I think we, as leaders across the different institutes, I think we're having the right conversations. Now we just got to turn them into real actionable programs.
I see. If are there other questions from council? Otherwise, I have a question, Eric. If I can go ahead and ask you. So I like your bold predictions, and one of those bold predictions has environment into it. So I think, in fact, my prediction is that maybe one of our bold predictions will be pretty similar to one of your bold predictions. But it's the question that I have for you is, as I indicated in my introductory comments, I really applaud you for your leadership in really bringing genetics and genomics, into the fore of, really weaving it into the fabric of the way we study the etiology of human disease across the biomedical spectrum. So I'm very interested, working together with my colleagues at NAEHS, working with you and others, to be doing the same thing, bringing greater awareness to the environment. What are some of those environmental triggers that actually may be responsible for taking someone with a genetic predisposition, but the environmental trigger that actually triggers the development of the phenotype? Also, in the context of the exposome framework, can we identify different environmental exposures that can mitigate some of the negative effects? So say someone is genetically predisposed, are there things in the environment that can mitigate them, to ultimately developing a disease?
Right. And we know that's true for children with, where you have to carefully watch what they eat. I mean, we already know that that's true. We're just scraping the surface. So I of course violently agree with you. I should point out, I should point out, I mean, I know I'm speaking to advisory council, and council members come on in 5-year interval, blah, blah, blah. I would contend, and it's no disrespect to previous leadership, I think it has to do with scientific opportunity. So there's nothing about previous leaders of our two institutes. There's just hands down, the interactions between NHGRI and NAEHS are at an all-time high. Just no question. And I'm not taking credit. I don't think, I mean, it has nothing to do, because we each respect our predecessors. I just think we've seen over the last 3-4 years, and increasingly, the scientific opportunities at the interface of the two institutes, and we're really working and looking and talking and strategizing, including our staffs, which are even more important. That's just not just Rick and I, to look to really capitalize on this. So, I couldn't be any more optimistic now that we're going to start to do some of these studies together, and we already are. And it is more and more partnerships are developing between the two institutes.
And we will continue to do that. One specific question, Eric. Yeah. So when you look at the genetics and genomics, the Human Genome Project was a real catalyst, I think. Would you agree with that?
No question.
So a project, at a beginning and an ending, it really triggered the creation of a data resource that helped to fuel all of the things that are happening in genomic medicine. How important will it be in the environmental health sciences community to create something the equivalent of the Human Genome Project, say the Human Exposome Project? Really to bring that visibility and greater awareness. What are your thoughts about that?
Yeah, my thoughts are, ever since the Genome Project sort of came into people's conscious, there's been lots of things that have been proposed at NIH. Some of which, well, we should organize that, the Human Genome Project, and I think each of those should be looked at very carefully, because I think some projects are more, and I think there's some important lessons learned from the Genome Project, including very well-defined quantitative goals. One of the things I was at the table when we made the decision with Francis Collins was, the Genome Project was originally supposed to be 15 years. We had these goals. We saw the goals were completed. We could have moved the goalposts and just kept keeping the project going. We ended the project 2 years early. And one of the things I think, and there's been various other things that have come up along the way where people said we should organize it like the Human Genome Project. I'm not so sure. It depends. I do think you got to decide whether or not you could really define it and a beginning and an end. And if it really seems way too overwhelming, it's all expansive, you may want to just not quite frame it that way, because then it sounds more like a long-term program as opposed to a discrete program. So, and we've done all sorts, we continue to do these big managed programs. But, even our human pangenome program, we said we're going to do 400 reference genomes, boom. We try to keep it very discreet. We know when we'll be done. So think about if you know exactly what you're trying to accomplish, if you're going to package it as part of a true big program like the Human Genome Project.
Terrific, great. Thanks very much, Eric. So let's see, are there any other hands coming up? If not, we're just about at time, and I know that Eric's got to jump in a Uber or something and get off to the airport.
Thanks very much, Rick, for the invitation. And it's been really wonderful talking to all of you. And if you have any questions or any follow-up, always feel free to email me.
Great.
Thank you,
Thanks
Eric.
again,
Great
Eric.
talk.
Okay.
All right, take care.
Take care. Okay, bye. Okay, David, back over to you. It looks like we're just about on time, maybe 5 minutes ahead of schedule, which is good.
We are just a little bit ahead of schedule, and I think we're going to shuffle our agenda one more time. Since we took a break earlier, I think we're going to go ahead and I'll turn it over to Daryl to introduce Dr. Ryder.
Thank you, David. So it's my pleasure to introduce Dr. Lisa Ryder. So Lisa is a senior clinician and head of the Environmental Autoimmunity Group in the Clinical Research Branch at NAEHS. She received her medical degree from Duke University School of Medicine and then completed her clinical training in pediatrics and pediatric rheumatology at Seattle Children's Hospital at the University of Washington. She then completed a postdoctoral research fellowship in the laboratory of Dr. Henry Metzger at NIAMS. Under the direction of Dr. Fred Miller, the Environmental Autoimmunity Group was established in 2001 as the first clinical research group at NIEHS that was located at the Clinical Center in Bethesda. Lisa became the deputy chief of that group in 2004, and she served and serves now as the senior clinician and head of the group since 2021. Dr. Ryder's research is focused on juvenile myositis, in which he's led a number of studies that have defined the major clinical and autoantibody phenotypes and their associated outcomes, identified genetic and environmental risk factors for disease, and led to the development of validated outcome measures and clinical trial response criteria. And she's led clinical trials of new biologic and other targeted therapies for both juvenile and adult myositis patients. She's published over 180 peer-reviewed manuscripts, many of which have appeared in the top journals in her field. She's received a number of awards in recognition of her contributions, including most recently being elected into the American Association of Physicians and receiving the American College of Rheumatology Excellence in Investigative Mentoring Award for distinction. She is an outstanding mentor, has successfully led trainees into tenure-track positions, particularly physician scientist trainees, and also serves on a number of national and international advisory committees. And so I'm going to turn the podium to her now. The title of her talk is Genetic and Environmental Risk Factors for Myositis Phenotypes Across the Lifespan. Lisa?
Okay, thank you so much, Daryl, for the very warm introduction, and thank you for the invitation today to speak. Okay. Okay, so I'm delighted to speak on genetic and environmental risk factors for myositis phenotypes across the lifespan. To take a step back, autoimmune diseases are a large public health problem that are really a growing public health problem. These diseases are defined by pathologic inflammation associated with autoantibodies against self-directed T lymphocyte responses. And the pathogenesis involves chronic immune activation after environmental exposures in genetically susceptible individuals. These diseases have a high and growing public health burden and now affect over 8% of the population in the United States. There are over 140 acquired disorders and up to 25 million persons are affected. And these are chronic, incurable, lifelong illnesses with significant morbidity, disability, and secondary health consequences. They have life and organ-threatening complications and are very costly. There is also a female predominance of these diseases even pre-pubertally, with 80% of the affected patients being women. And it's recently been recognized by the National Academies of Sciences that these diseases are understudied, and recently a formation of an NIH Office of Autoimmune Disease Research to better coordinate autoimmune disease research across the NIH. Fred Miller's study with the NAEHS data from the CDC, a population-based US cohort, suggested there is a rapid rise in anti-nuclear antibody presence from 11% to 16% over only a few decades. This is particularly prominent in men and in adolescents and older adults, as well as in non-Hispanic whites. And as many as 33% of these adults, particularly who are older, had a disease-specific autoantibody, suggesting they don't just have autoimmunity, but they actually have autoimmune disease. There's also population-based data from the United Kingdom suggesting 10% are affected now with an autoimmune disease, and as many as 19% of the women. And the incidence rates are rising over the past 2 decades, and this is even pre-COVID data. This is true for both organ-specific diseases as well as systemic autoimmune diseases, with particularly rapid rises in celiac disease, Graves' disease, and Sjogren's syndrome. The Environmental Autoimmunity Group is part of NIEHS, but we're located here on the main campus in Bethesda at the NIH Clinical Center. We were established about 20 years ago to focus on understanding the role of the environment and genes and their mechanisms in autoimmune diseases, with the ultimate aim of disease prevention. Through these studies, we have developed the largest myositis databases and biorepositories in the world, with over 3,500 clinically well-characterized patients. We conduct natural history studies that focus on genetic and environmental risk factors, as well as therapeutic trials of novel biologic and other therapies. We have several studies that we've performed here. Our first one is a national myositis patient registry we call MyoVision, which was a partnership with the Myositis Association and Cincinnati Children's Hospital. And we here are trying to understand myositis phenotypes and had more than 2,000 patients enroll from throughout the country. Our twin sibling study of systemic autoimmune disease enrolled more than almost 300 discordant twins and siblings, where a proband developed a systemic autoimmune rheumatic disease within the past 5 years, and they had a same gender healthy sibling, and their parents also enrolled when possible. And then we have other cohorts, an anti-synthetase syndrome cohort focused on risk factors for myositis and interstitial lung disease, which patients enrolled closer to the time of diagnosis with matched controls, and a military myositis study as well, looking for specific exposures in that unique population. Myositis is a heterogeneous group of systemic autoimmune diseases, but have an attack on the muscle with chronic muscle inflammation and the development of unique autoantibodies in these diseases. These are rare diseases, but they are still the most common acquired chronic muscle disease in the United States. And there are different forms of the disease. One form, dermatomyositis, has characteristic skin rashes and a primary attack on the muscle blood vessels or endothelium. Polymyositis, more T-cell mediated, with the attack more directly on the myofibers. And inclusion body myositis, more in older men. These are very debilitating conditions with chronic functional disability, weakness, and other complications. And they're very costly, as are our other autoimmune diseases. Our studies have been focused on parallel studies in adults and children to identify similarities and differences, not only in the clinical spectrum, but also in the genetic and environmental risk factors. So we have studied adult and juvenile dermatomyositis in parallel, a disease that affects 30% of adults with myositis, but 80% of the children, while other forms are more frequent in adults, including inclusion body myositis in older men, immune-mediated necrotizing myopathy, where there's more muscle necrosis and very severe muscle involvement, and polymyositis, affecting more the lungs and heart. These diseases share many clinical features in children and adults, but in adults, there's more increased risk of malignancy associated with dermatomyositis, interstitial lung disease, more common in the adult patients, as well as cardiac dysfunction. In the children, we see calcinosis more frequently, a deposit of subcutaneous calcium in the soft tissues, and vasculopathic features such as ulceration in the skin or gastrointestinal tract, and loss of body fat, called lipodystrophy, that may lead to metabolic sequelae. Both forms have functional disability, a chronic illness predominance, and increased mortality, but the adults, this is even more the case and less responsiveness to treatment. And we think that these diseases share many genetic risk factors and environmental risk factors, but that there are some distinctions by these phenotypes. We've also come to understand through our work and others that myositis autoantibodies are present in 50 to 70% of patients with these illnesses. And these are autoantibodies that are directed against cellular proteins that are involved in translation and transcription and are actually present in all cells, but increased in expression in regenerating myoblasts. They are antigen driven in that they arise prior to the illness onset, and the titers vary with disease activity. And these specific antibodies in myositis are mutually exclusive in that patients have only one of these. There is an emerging role of these autoantibodies in disease pathogenesis, with much of this work by my colleague Andrew Mammon from NAEHS, and some of this work we've done in collaboration as well. He is seeing a very strong type 1 interferon response in patients with dermatomyositis with the dermatomyositis specific antibodies, an intermediate for Jo1 or the anti-synthetase antibodies, and no interferon response in the other subgroups, while type 2 interferon response is seen in many of these subgroups, including the necrotizing myopathy form. He's also finding that these autoantibodies can enter the myoblasts and then inhibit the target autoantigens and induce cellular stress and inflammation. Here, for example, with MI2 autoantibodies, when transfected into cells, these antibodies induce the NERD complex of the target histidine deacetylase that they target, and that there's a transcriptional de-repression of many different inflammatory genes, so that this is contributing to disease pathogenesis. There are also emerging mouse models of different target autoantigens that are recapitulating the features of the human disease. So these autoantibodies seem to have a role in pathogenesis. They also have defined specific phenotypes, and this is based on our studies of large cohorts, both from here at the NIH and a nationwide childhood cohort that we have set up through our NIH studies. And we can see, for example, that they define very specific clinical syndromes with these different autoantibody subgroups. So the anti-synthetase syndrome directed against tRNA synthetases has a high prevalence of interstitial lung disease, along with systemic features like mechanics hands, arthritis, and Raynaud's and fevers. There are different autoantibodies associated with dermatomyositis, some of them highly associated with the photosensitive skin rashes, and others more with the severe muscle manifestations and calcinosis, and certain of these antibodies in adults associated with malignancy. And then antibodies associated with the necrotizing myopathy, very severe form of myositis with proximal and distal weakness and severe disability. Dr. Mammon defined one that's associated against the HMG-CoA reductase and associated with statin therapy. And we see other antibodies called myositis associated that are seen in other autoimmune diseases that are highly associated with lung disease. And we'll come to talk about these different phenotypes more. Our hypothesis is that we have different phenotypes of myositis, now being defined by different autoantibodies, that there are different genetic risk factors. Some of them will be specific to specific phenotypes, and some of them shared among phenotypes or even among other autoimmune diseases. And that there will also be different environmental factors that we could define, again, some shared and some may be specific. So our goal ultimately is to define the specific environment gene phenotype interactions here. Why would we study genetic risk factors for myositis? To identify those that are similar among myositis patients that are risk factors for myositis, but also that there may be some shared similarities to other autoimmune diseases. This will give us insights to biologic pathways of disease and may suggest new targets for therapy or even prognostic biomarkers. Fred Miller started this work several decades ago. It was a family study of autoimmune disease, taking patients with myositis and looking at their first-degree relatives as well as control subjects, and finding that the probands with myositis, they had 22% in their families with another family member with autoimmune disease, a first-degree relative with autoimmune disease. So a highly increased risk of autoimmunity in these families, with a spectrum of autoimmune diseases represented, and the most frequent in the population, the most commonly represented of these. His study suggested a polygenic mode of inheritance. And this data were confirmed in a US national JDM registry from Lauren Pachman, as well as a Swedish National Healthcare Registry study. And they also saw increase in lupus and celiac disease in these relatives of myositis patients. Individuals with myositis were found to have 4.3 times more likely to have a first-degree relative with myositis compared to other people, and then that they had 2.7 times more likely to have a sibling with myositis, but that the heritability of myositis was relatively low, was only found to be about 22 to 24%. Our group at first studied HLA risk factors, focused on these polymorphic genetic loci that would present antigens from the immune system, from the environment to the immune system. And then we went on Fred went on to form an international genetics myositis cohort that did GWAS studies. These different GWAS studies and immunochip studies have defined the 8.1 ancestral haplotype as the major risk factor for all forms of myositis, dermatomyositis in children and adults, as well as polymyositis and inclusion body myositis. And there's an extended haplotype, although the DRB10301 and B0801 are the strongest risk factors in these different subgroups. There are also different risk factors in the different autoantibody subgroups, and this is now isolated to specific amino acids along the peptide binding groove, or which may be near the peptide binding groove and affect the conformation of antigens that bind in the groove. Some of these are shared among different autoantibodies, and some of them are unique to particular autoantibody, and some, like Jo1, have several different residues that are associated. And we could see that the risk factors for children and adults are largely the same, but that there are slight differences. For example, there's also a C allele in the children that is a strong risk factor. And for example, in the TIF1 gamma autoantibody group, just very slight differences in the risk of the DQB1 allele. With larger numbers of patients, an addition of patients from the US and Europe, additional risk factors have been identified across the genome. And interestingly, many of these may play a role in pathogenesis, and some of them are immune response genes. Here are just some of the major findings from these different studies. Some of the PTPN24 and STAT4 are two SNPs that have been identified that really have roles in T cell function and are particularly risk factors for polymyositis. I might also point out that all of the risk factors identified are also shared with a number of different systemic autoimmune diseases. There are risk factors for myositis overall that are involved in general cell signaling or protein degradation, or also the interferon pathway, which stimulates type 1 and interferon gene. In dermatomyositis, there are other cell signaling genes, or gasdermin B, which promotes programmed cell death, as well as B cell receptor signaling and T cell receptor signaling genes that are thought to be involved in pathogenesis of dermatomyositis. So these studies are ongoing, and we are continuing to work on the genetics. So turning now to the more important side of the equation, the environment, what would be the evidence for environmental influences in autoimmune diseases? First, these diseases have low to moderate disease concordance in twins, and that the major genetic risk factors are also environmental response genes. There's biologic plausibility from in vitro and animal studies, and that there's strong temporal associations with some exposures and disease onset. We can see seasonal and geographic clusterings in time and space with disease onset and increase in incidence over time. For certain of our drugs or biologics, we also have seen patients who are exposed to a particular drug or biologic. Their disease improves after it's taken away, and then when re-exposed, disease recurs or persists, suggesting strong association. And then case control studies have been done to firm up these exposures and their association with disease risk. So our hypothesis is that patients have underlying genetic risk, that they have exposure to environmental exposures, a variety of kinds, and can develop preclinical autoimmunity and inflammation that would not yet be a actual disease. And then that they have initial signs of clinical disease after additional environmental exposures or hits, finally reaching a classifiable disease. But we also think these environmental agents may not only initiate disease, but even may advance or sustain disease or even flare disease. And we have some data to suggest this as well. We also hypothesize that there are different exposures at different periods in life and important periods at different developmental stages in utero or perinatal, early childhood, adolescence, and adulthood. These exposures may include infections, hormone, nutritional factors, the microbiome, sunlight through UVB, smoking and air pollution, occupational exposures, and others. And we'll come to talk about some of these as we are beginning to understand their risk for myositis. And again, we see a pathway of immune dysregulation, setting up inflammation, autoimmunity, and finally clinical autoimmune disease. So through our National Myositis Patient Registry and our collaboration with Munir Hussain, an epidemiologist at Cincinnati Children's, he used spatial modeling to define the characteristics of the geographic locations of the patients in this registry, the largest patient registry in the country. And through these black dots, you could see a higher increase in myositis cases in the East and Northeast, which was true for different subgroups of patients, dermatomyositis and inclusion body myositis, an increase in polymyositis in the South, which I'm not showing you here. The cases also clustered so that with dermato and polymyositis, there was about 100-kilometer distance between them, whereas the inclusion body myositis a little bit further, on average 150-kilometer distance. We could also see, looking at the different subgroups of cases, that there was an increased prevalence of dermatomyositis here in the West and decreased in the Northwest, where there's lower UV exposure. There was also an increase in patients with lung disease in Texas compared to other regions, and again, lower in the Northwest. There was also a roadway analysis in this study suggesting that patients with myositis, particularly inclusion body myositis, the form in older patients, were living closer to major roadways, although this was probably not a large enough cohort to see the true effects. We also see season of onset and clustering in our certain different autoantibody subgroups. So in adults and children, we've seen a spring season of onset in the anti-synthetase patients, the patients with the lung disease, and a more late spring, early summer onset in the children. And this was particularly prominent in men with polymyositis in the adult patients, a larger cohort. While the antibody negative patients, the adults had more of a summer of onset, stronger in women with dermatomyositis, and in children, no seasonal predilection. And for our other autoantibody groups, we have not seen a particular season of predilection. We've gone on to do studies about UV radiation, seeing from our national patient registry that the patients with dermatomyositis, the form with photosensitive skin rashes, particularly had an increase in sunburn in the year prior to diagnosis, not only relative to the patients without these photosensitive skin rashes, but also relative to healthy population through the CDC data. And then through our exposure questionnaires, we could see the sun exposure appeared to be related more to jobs in men and hobbies in women. We then went on to look at the residential locations of patients, looking at their UV exposure through the TOM satellite data, and could see an increase in UV radiation exposure proportionate and more dermatomyositis cases with more UV radiation exposure at different locations throughout the world. This is a study led by Fred Miller. So the equatorial regions having the most prevalence of dermatomyositis relative to other forms of myositis. And that in the northern most latitudes, like in Stockholm or Glasgow, much less UV exposure, much less dermatomyositis. This study was replicated in the United States using more specific data within a year of diagnosis, and the association was seen more again with dermatomyositis and with MI2 autoantibodies, a dermatomyositis-specific autoantibody, and again more in women and in white patients. In the children, we also took a look at this and now could see associations with not only dermatomyositis in children, but TIF1 gamma, the most common autoantibody subgroup in children, which is highly associated with the photosensitive rashes. We also see this association with another autoantibody group in the children with dermatomyositis, but not in the antibody negative patients or in the patients who have more of a prominence of muscle disease. And we see again more of a female predilection for this association with UV radiation. Fred went on actually with Trevor Archer to do studies in vitro and to look at the expression of MI2 autoantigen with stimulation of UV radiation, finding increase in message production following the end protein translation and increased message stability with exposure to UV radiation in vitro. Looking at another environmental exposure, we've gone on in our twin sibling study. Yasmin Bauer-Ventura, a collaborating rheumatologist, and our student Maya Goldberg have looked at stressful life events in the year prior to diagnosis using a validated questionnaire to capture these events and querying patients about the year prior to diagnosis, finding particularly in the adult patients that the number of events, particularly uncontrollable or undesirable events, as well as their negative reaction to these events, including for major events, was increased in frequency and in risk for patients with myositis compared to healthy controls, and intermediate in risk in the unaffected siblings. Stress has been seen in other studies, although not studied so systematically. This Swedish registry study has found that patients who had traumatic, stressful events in their life, in the 10 subsequent years, they were more likely to develop an autoimmune disease of a variety of different kinds, with the overall risk being increased by about 1.4. And that for people with post-traumatic stress disorder, they had even more increased risk and were more likely to develop up to 3 of these different autoimmune diseases. We turn next to occupation and hobby exposures, again through the National Patient Registry. And this work was led by epidemiologist Christine Parks from the epidemiology branch. We have an occupation and hobby questionnaire capturing the jobs that patients held prior to their development of myositis. And these data were coded independently by 2 occupational epidemiologists and a student of ours with a Master of Public Health degree who were blinded to the clinical data. So they were able to code the occupations and what exposures those linked to. Here they saw particularly a high silica dust exposure was associated with dermatomyositis compared to inclusion body myositis, and that the patients with lung disease, particularly having an antisynthetase-like phenotype, they had lung disease with arthritis and fever, and as well as patients with overlap myositis who have myositis with another autoimmune disease. These patients particularly, when having a high silica exposure, were more likely to have these forms of myositis. This was particularly increased in patients who were smokers as well. So smoking interacted with this risk of silica exposure. We also saw, and not shown here, that moderate to high heavy metal exposure and also solvent exposure increased the likelihood of having the lung disease phenotype, the antisynthetase phenotype, as well as with overlap myositis, which also have a higher incidence of lung disease. And again, that smokers with this have higher frequency of a likelihood of this complication. We were also interested in infection as potential etiology and approached this question first with Ben Larman's group, trying to look at the antibody responses through a methodology called FIP-seq, where he can take different peptides and create peptide libraries, expressing them in bacteriophages, and then immunoprecipitating patient sera and looking at the peptides that are reacting. He has a library of bacterial and pathogen peptides and human commensals, as well as a virome peptide library. So looking at the bacterial and commensal library, we particularly saw that there was an increase in reactivity to flagellin peptides, particularly from species like Helicobacter pylori or Burgdorferi, the infectious agent of Lyme disease. These were increased in patients with dermatomyositis compared to a vaccine-related control group from NAEHS. These flagellin peptides are increased in the gut and found to have a role in gut motility. And interestingly, the patients with these peptide reactivities had consensus sequence that was conserved among these different bacterial peptides. They also validated that the activity was specifically to flagellin in a mesoscale diagnostics assay, seeing that almost half of the patients with juvenile dermatomyositis were flagellin positive, whereas only a quarter of the controls were flagellin positive, and that the patients that were positive, interestingly, were all younger children, and those positive for the TIF1 gamma, the most common autoantibodies in the children. Given that flagellin has a role in gut bacteria, we went on to do a study regarding microbiome, oral microbiome, and stool microbiome using our twin SIB cohort, and did this study with our investigator colleagues at University of Washington, Neil Day and Ann Stevens groups. Here we could see in our families where probands are affected with juvenile dermatomyositis and they have a healthy sibling, that in the stool microbiome, that there was a good commonality between these probands to their healthy sibling, and this surprised us compared to probands to their parents or siblings to their parents. Whereas juvenile dermatomyositis probeans, and this was a study done both here at NIH and at University of Washington, these probands were more similar to each other than other relationships within the family. In the oral microbiome, however, there was more shared microbiome among the different family members, perhaps related to shared food products in the home and shared utensils. And while still probands with juvenile dermatomyositis had more similarity in their oral microbiome compared to other relationships. The probands with juvenile dermatomyositis had overlap, but a slight difference between the NIH cohort and the Seattle Children's cohort. But these cohorts were different than other published healthy control cohorts that were using similar methods to study gut microbiome. And then there were some species that were differentially expressed in the stool and oral microbiome. 4% of the stool species and 8% of the oral species in the subgingival dental plaque were differentially expressed. A number of these stool species that were increased, that are shown in red or in the oral, actually have had a role in other systemic autoimmune diseases. They've been seen to be increased there as well. Some of them have been known to be pro-inflammatory, generating pro-inflammatory cytokines or even promoting autoantibody formation. And so we think these species may have a role in autoimmune dysfunction. Some of these species also were increased and are known to have flagellum-containing bacteria as well. Fred Miller and his postdoc Lou Gann several years back also looked at our twin sibling cohort, looking for evidence of viral response and seeing a strong antiviral signatures or interferon signatures and pathways related to interferon in patients with systemic autoimmune disease, not just myositis, but the patients with other systemic autoimmune diseases as well, that these pathways are upregulated. And they did a study looking at viral array, looking at 54 different viral families, and finding that 40 viral families and 64 different viral probes had increased expression in our patients with systemic autoimmune diseases as compared to the unaffected siblings or healthy controls, although the unaffected siblings were intermediate with compared to the healthy controls and the probands. There was no increase in expression in certain viruses that we thought would be increased in patients with autoimmunity, like Epstein-Barr virus, pyrovirus, or varicella, but they did see reactivity to 3 different genes to herpes simplex virus 2. This was increased in probands as compared to unaffected siblings or the healthy controls. And these are treated patients, so we don't know if these are related to treatment or to disease onset, although notably several other groups are now reporting about herpes virus infection associated with systemic autoimmune diseases. We're also interested in the relationship then of the specific phenotypes and exposure and genetic risk factors. And this is an interesting study led by Adam Schiffenbauer, who's our adult rheumatologist and deputy head of the group now. Adam found that in our cohort, particularly our Meyer risk cohort, that the patients with polymyositis and patients with lung disease were more likely to have a risk factor for smoking. And this was particularly true in Caucasian patients, not in African American patients. He also saw this risk to be increased in patients with antisynthetase syndrome, specifically the form with lung disease, that smoking was a risk factor for this form of disease and not for the other autoantibody subgroups. Adam then went on to look at the interaction of HLA with the smoking and saw an even increased risk of both HLA, DR beta 1, O301, the risk factor for myositis overall, and for the antisynthetase autoantibody subgroup specifically, that this with smoking had a particularly increased risk of this phenotype compared to HLA by itself or smoking by itself. Similarly, another gene environment phenotype interaction is defined by the immune-mediated necrotizing myopathy group, the group that has severe muscle weakness and a lot of muscle necrosis on biopsy with little muscle inflammation. And this group of patients in adults is, which is a common group in adult myositis, is highly associated with statin exposure, either drugs that are statins or dietary statins, such as red yeast rice extract or oyster mushrooms as 2 sources of dietary statins. My colleague Andrew Mammon has found a strong risk factor for this statin exposure in these patients with necrotizing myopathy, with the HLA DR beta 1 1101 allele to be a strong risk factor for this subgroup of patients. And then in children with myositis, this is a much rarer form of myositis in children. The same clinical features are present in children and adults and the same biopsy features, but we have not found any association with statin medications or dietary statins in the children. And we see a completely different HLA risk factor in the children as compared to the adults. So we have also then been interested in whether some of these environmental exposures might be related to disease flare or disease course. We conducted one study with our colleagues at George Washington University with my former fellow, Gulnara Mamrarova, looking at patients with dermatomyositis, 2/3 of whom flared as defined by a physician confirming their flare and that they had to increase medication. This was a questionnaire-based study. And we asked them about a number of exposures that they had in the 6 months prior to their flare, finding that a number of the same exposures that we were seeing related to disease onset might also be relating to disease flare. So that sunburns were increased in the group that flared, certain infections like gastroenteritis and urinary tract infection, and exposure to certain medications as well, non-steroidals, blood pressure medications, or medications for depression. We've also looked at certain exposures in relation to disease course, and in data that I'm not showing here, we find that infections in the 6 months prior to disease onset are particularly associated with a chronic illness course in the children, and that a higher UV exposure is also seen in the 30 days prior to illness onset in the group with the TIF1 gamma autoantibodies. So in summary then, we are beginning to define a number of different environmental risk factors for systemic autoimmune diseases and for myositis, and we can see some differences in these factors by different subgroups of patients. Psychosocial stress as a factor for systemic autoimmune rheumatic diseases and myositis overall. Certain infections like SARS-CoV-2 infection in dermatomyositis or commensal gut bacteria, perhaps in juvenile dermatomyositis. Ultraviolet radiation, a strong risk factor in our dermatomyositis patients and the autoantibody subgroups associated with photosensitive rashes. Smoking, pollutants, and silica and heavy metal exposure in the patients who have lung disease, so polymyositis, antisynthetase phenotype, or overlap myositis patients. And then the statin exposures with the immune-mediated necrotizing myopathy. We're beginning to see that certain of these exposures have certain HLA risk factors, and that these, from this work and others' work, we could see that some of these exposures might be setting up certain pathways that are pro-inflammatory or certain key pathways such as interferon response in these patients with dermatomyositis, that certain autoantigens are upregulated with these exposures, such as with UV radiation or with antisynthetase with smoking and with the statin exposure as well. So we think that these exposures link to pathogenic pathways as well. So this, I would say, is our circle of interaction of phenotypes that we defined in our work, genetic risk factors that we've begun to define, and then the environmental factors, medications, infections, beginning to look at lifestyle and geographic exposure as well, and that we're beginning to try to put these together to link exposures, genetics, to specific phenotypes of myositis. So what have we learned from this work? That we see that genetic risk factors are important, but that the rapid rise in autoimmune diseases and other data strongly implicate the environment. That the 8.1 ancestral haplotype is the major risk factor for myositis and the major subgroups of myositis, including many of the autoantibody subgroups, but that there are different HLA risk factors with different antibody subgroups, and that there are different immune activation and cell signaling genetic risk factors that suggest additional pathways of myositis that are shared with other autoimmune diseases, and these have implications for targeted therapies. We are beginning to define different environmental risk factors for myositis phenotypes, including UV radiation, psychosocial stress, and certain infections, as well as medications. And in adults are able to link tobacco use and occupational exposure to particularly the form with lung disease. We see also gene-environment interactions beginning to emerge of myositis autoantibody phenotypes or interactions with these specific genetic and environmental risk factors, and that certain exposures may influence the disease course as well and disease flares. Our future work is continuing to define more rarer variants of myositis genetic risk factors through whole exome, whole genome sequencing approaches, looking at multiple family members. These are rare families where more than one relative has myositis, as well as in singleton families with certain specific antibody subgroups. We're using our different cohorts to look further at our environmental questionnaire data and to look at GIS analysis to further define environmental risk factors. And then we are hoping to look at and define environmental and genetic and even G by E risk scores. We're looking at genome-wide epigenetic data as well as specific exposomic and metabolomic data to look at specific exposures that the patients have actually been exposed to. And we're looking at a preventive trial in the future focused on a dietary intervention that we hope to open in 2025. So our new approaches and technologies are allowing us to carefully define these myositis phenotypes, to define the genetic and environmental factors, and to look at their interaction. With our ultimate goal is to understand these factors, and we hope to prevent disease through altering the environment. I'd like to thank many members of our team, and particularly Fred Miller for leading us in this work for many years. And to Adam Schiffenbauer, our deputy head of the group now, along with a number of recent trainees. We have a number of collaborators in NAEHS who have made this work possible, including use of the core laboratories, and a number of collaborators throughout NIH and throughout our MyoVision registry, Myogen Genetics Consortium, and others. So thank you for your attention, and I'll be happy to take your questions. Thank you.
Great talk, Lisa. Wonderful example of some of the concepts that Eric Green just spoke about in terms of understanding gene-environment interactions. So the talk is open for comment or question from council members. Stephania?
So one of my questions is actually, do you think that the data that we're seeing with these large increases are actually due to better diagnostics?
That's a good question, but I think that the increases not just in the U.S. but in UK cohorts are really speaking, and the rapid rise. It's a more rapid rise, and there's, we know after COVID infection the rise went up even more. So that I think that it's more than the diagnostic.
And do you think that the increase, like you're seeing a lot of East Coast and West Coast, are there areas where you see there is less testing for autoimmune diseases where they might also be impacted? So for example, rural areas, which is
right, rural areas. We had some representation of rural areas in our national patient registry, but it is underrepresented, so to speak. It is hard to get to the rural areas. I think that's still an understudied area. I think there are opportunities to do certain studies in the rural areas. For example, a number of years ago, I was asked to go out to Libby, Montana with Aubrey Miller, and there was a conference there on the Libby Amphibole. And of course, all the focus was on asbestos exposure and the lung cancers that were developing, but they were starting to see a signal for autoimmune disease and autoinflammatory disease, and that prompted some looking. And in fact, Gene Fao has found a number of autoantibodies in that population. So I think we have to take advantage of these specific exposure opportunities to go and look at these rural areas.
Okay, thank you.
Gary?
Yeah, that last slide there that showed that integration, it's a great conceptual diagram, but like to my comments to Eric was the types of data we're trying to integrate, like the geospatial and the environmental with the genetics. Like what is your thinking about that? Because they're not easily integrated and we need to figure out how to do it.
Yes, I agree with you. And one of our problems, we study a very rare disease, and we have interesting data on portions of our cohort, but we don't have data on everybody, on, like transcriptomic, exposomic, genomic data. There are different portions of our cohort that have these different data. But I am working with the Norwegian mother-baby study, for example, where they really have opportunity to have to try to integrate the whole thing. And we're working with Claire Weinberg and Min Shi in the biostatistics branch to start to help them think about gene-environment interactions and start to think about this more broadly. So I think we need some different cohorts too to be able to integrate some of these data. I hope all of us will give us some of that opportunity as well.
Andre? Dr. Holian?
Hi. Thank you for a very nice comprehensive presentation. I guess my question is more focused on the contribution of inflammation to the development and the progression of autoimmune diseases. Obviously, silica is a great example of that, and working in collaboration with Mike Pollard, showing the connections between those two. So, could one speculate that if one could block the chronic inflammation, that would help resolve autoimmune disease? Do you think there's any where might that fit into the process?
Sure. I mean, I think that our current medications are targeted on suppressing the inflammation. And I do think that blocking these environmental triggers, my hypothesis is that would fit into the process. For example, and I have some patients that I've seen with this TIF1 gamma autoantibody who have a very high high number of photosensitive skin rashes, and just if they just step out into the daylight for 5 minutes, they're covered head to toe in skin rashes. So, really try to work with these type of patients to really work with them on photoprotective measures and blocking down their exposure to UV radiation through a variety of methods. And these patients, it's anecdotal, but they've been able to not only improve their symptoms of myositis, but also to get off a number of their immunosuppressive medications. So I do think that this could be a very important pathway to block this down. Yes.
I have a couple questions. So to what extent are you using the pharmacogenetic data that Eric talked about? Because I noticed a number of the drugs that are, where we have good actionable pharmacogenetic data are, treat autoimmune diseases. So to what extent are you using that data on a patient-to-patient basis to customize therapy?
There are really currently only a few examples where we use that data. For example, azathioprine, which is a drug that's not used commonly anymore. There are certainly fast metabolizers and slow metabolizers, and that one is perhaps our most important one to check on the pharmacogenomics before we start the treatment. But largely, we are not using that in the day-to-day clinic. Yeah.
And then the second question is, again, building on the theme that Eric, so if you were to make 2 or 3 bold predictions for what the field of myositis and gene environment interaction will go in the next 3 to 5 years, what are your bold predictions?
Well, one of them would be that we're just going to have to dig in and start to intervene on some of these environmental factors and see if we can improve patients' illness. And that's our hope. That's what we're going to do with our next study, trying to intervene on diet and also giving people omega-3 fatty acid, which through a study that the VITAL trial, that administration of omega-3 fatty acid prevented autoimmune disease. So we're thinking that this is going to be a pathway that will help to decrease symptoms of autoimmunity. So I think that's one area that I think will be very active. I think also better understanding the mechanisms here, and then trying to get down to those specific gene environment phenotype interactions, and then understanding the mechanisms there is a big area of growth for this field. And then the pre-autoimmune area, before disease starts, can we intervene in these at-risk families? So that's another very active area of research. But I think also the field is, and I'm seeing this push also from the NIH Office of Autoimmune Disease Research, they are helping to facilitate the funding of certain cohorts that are then going to be set up for exposomics work. And I think that area will grow, is to be able to, we're really some of the first people looking at environmental risk factors in these autoimmune diseases, but I think we're going to start to get everybody looking at environmental risk factors and seeing how that plays into these illnesses.
Great. So if there's no other questions from council, let me thank Lisa again for a wonderful talk and turn things back over to David.
Thank you so much. Very
Thank you, Daryl, and thank you again, Lisa, on behalf of Extramural. The great presentation, and I think it really falls very much in line with our theme for the day, so very much on point. We are about 10 minutes ahead of schedule, which is an unusual place for us to be. So I think what we'll do is we'll go ahead and we'll take our lunch break now. And we'll reconvene at 1 p.m. Eastern time for our mini symposium, digging into some more of the substance of gene-environment interactions. So with that, I will say thank you all, and we'll go on break for the next 55 minutes.